Hello everyone, Kotongwane the Nated God here. This year is a video based on line shafts, a topic we find in Mechanotechnics N6. As you know, this year is part of a series of videos I am doing to cover the topic. If you are tuning in for the first time, just make sure to watch the two videos that precede this one. The link you will find in the description. Right. Otherwise, if you've watched both of those videos, then you are in the right place. Right. So on this video, I will take you through how we make use of the forces that each of our mechanical systems are subjected to. That's how we get to use those forces in calculating the reactions at the bearings, be it on the vertical or the horizontal plane. Right. First, let's look at the statement and take from it our given data. Right. So the statement reads as follows: the transmission shaft shown below, so essentially this line shaft, is driven by a pinion rotating clockwise. Right. So the drive shaft is fitted onto the pinion, and the pinion is rotating clockwise and transmitting 200 newtons. So that is to say that if the pinion is our input, or is fitted with the input shaft, and it's transmitting 200 newton meters, then it means our input torque is equal to 200 newton meters. The PCD of the pinion is 300 millimeters. So the PCD of the pinion is fitted with the input shaft, so we can take this as PCD in is equal to 0.3 meters. The efficiency of the gear drive, so we have the efficiency of the gear system of the gear drive is equal to 70%, that is 0.7, and then the gear ratio is 4:1, which essentially is equal to 4. The diameter of the belt pulley is 420 millimeters with a contact angle of 160 degrees. So the contact angle of the pulley that is fitted onto our transmission shaft or line shaft is 160 degrees, which is obviously less than 180 degrees, which means our angle of contact is taken from, or the pulley that is fitted onto the line shaft is the smaller pulley, right? So which means the diameter is for the diameter of the smaller pulley, which is 420 millimeters, that's 0.42 meters. And then our angle of contact, as we've established, is for the small pulley is 160 degrees. Tension ratio is 5:1, which means essentially T1 over T2 is equal to 5. And then they've also given us the mass of the flywheel. So I'm going to call this MF for mass of the flywheel is equal to 200 kilograms. Now just bear in mind that the flywheel is essentially a energy storage unit, right? So the only force that a flywheel really is subjected to is its weight, right? So the only force to consider as far as the flywheel will be its weight. So that is to say that we'll only consider the weight when looking at calculating the reactions at the bearing in the vertical plane, right? But when looking at the reactions at the bearings on the horizontal plane, because there's no component of the weight that is parallel with the horizontal plane, right, there won't be a force to include as far as the flywheel. All right, now let's look at 4.1. 4.1 is said calculate the normal force. Right, as you know, the normal force is the force that we get, right, in gear systems. So where the pinion and gear wheel come into contact, that is where you get your normal force. So they want us to calculate the normal force here. The way you can calculate your normal force, we know there's a number of ways, but whatever you calculate will always be based on the information that you've been given. So here you are given the input torque as well as the PCD of the input gear, the pinion. Right, so you simply use the formula to calculate torque, which is the tangential force times the radius of the input gear. Right, so seeing that we have the PCD instead, we can say that this is the PCD of the pinion, so the input gear divided by 2. Right, so from this we want to calculate the tangential force. We have this, so you simply make the tangential force the subject of the formula, and in doing so, Ft will then be equal to the input torque times 2 divided by the PCD of the input gear, the pinion. All right, now you substitute. Input torque is 200 Newton meters. So that's 200 times 2 divided by the PCD of the pinion, which is 0.3. Right? And then if you punch this in your calculators, you should get 1333,333 newtons. Right? Now this here is the tangential force. But remember, we are looking for the normal force. Right, so in calculating the normal force, right, remember that when considering all three forces subjected to the gears in mesh, you have your radial force, you have your tangential force, and then of course you have the normal force, which acts at 20 degrees from the horizontal. Right, now this of course is if you're just considering the Cartesian plane of the gear system on its own. Right, the normal force will be acting at 20 degrees. This you should know, having covered bearings in Mechanotechnics N4. Right, now based on how these three forces are acting, right, there is a number of ways in which you can calculate normal force. Right, and how you calculate the normal force will depend on what it is that you've been given. So in this case, we have the tangential force, so we'll use the relationship between these two to calculate the normal force. Right, so bearing in mind that the normal force essentially is the hypotenuse, right, it means that essentially Ft is going to be equal to Fn times cos 20. Right, so bearing that in mind, it means to calculate the normal force is equal to the tangential force divided by cos 20. Right, and then you substitute your tangential force, which is 1333,333 divided by cos 20. Right, and then punching this in our calculators, we get 1418,903 newtons. right? And there you have your normal force, right? Next, we look at 4.2. Right, so 4.2, they want us to calculate the torque transmitted by the counter shaft. So counter shaft, transmission shaft, line shaft, same thing. So when they want you to calculate the torque transmitted by the counter shaft, they want us to essentially calculate the torque being transmitted by the line shaft, which essentially means to calculate the output torque. Because remember, the input torque, seeing that the input shaft is fitted on the pinion, we've already calculated. In fact, it was given to us. So when having to calculate the torque of the torque transmitted by the counter shaft, they want you to calculate the output torque. Right? Right. I don't know what I did here. Okay. So this is 4.2. They want us to calculate the output torque. Now, in calculating the output torque, you look at what you've been given, right? And as far as what you've been given, you have the gear ratio, and you've been given the efficiency of the gear system. Now, remember that there's a number of ways in which you can express the gear ratio. You can express the gear ratio in terms of the rotational frequency. You can express the gear ratio in terms of number of teeth. You can express the gear ratio in terms of the PCD. You can express the gear ratio also in terms of the torque, right? In terms of torque. And in terms of torque, the gear ratio is equal to T out divided by T in. Now, clearly here, our gearing system is not 100% efficient. So also taking into consideration the efficiency, you take that efficiency and multiply it to T in. Right, this you should already know from having dealt with gear systems in N4 as well as in N5. Right, and then from here we are looking for T out, so we then make T out the subject of the formula. Hence this will be equal to the gear ratio times T in times the efficiency. Right, now you substitute. The gear ratio is given to us as 4, so that's 4. Input torque, remember, is 200 Newton meters. Efficiency 70%, so 0.7. Now if you punch this in our calculators, we get 560 Newton meters. Right, and that becomes our output torque. Right, now having established the output torque, right, that means having established the output torque, right, on the or being transmitted by the line shaft, it inadvertently means you have the output torque on the belt drive, the output torque of the gear drive as well. So of all the systems that are fitted onto the line shaft, right, you inadvertently have now calculated the output torque for all of them. Right, so meaning you are able to, if push comes to shove, use the output torque we've just calculated to calculate any one of the quantities that we can use torque to calculate. Right, so just bear that in mind. Now looking at 4.3, they want us to calculate the belt tensions. right? So we are now at 4.3. 4.3. They want us to now calculate the belt tension, right? Now there's a number of ways you can calculate the belt tension. Again, you look at what you have to make the determination of how to approach 4.3 in calculating belt tensions. Now we've been given the tension ratio, right? We have two unknowns, T1 and T2, which means we are going to need two equations. One of them they've already given us essentially, right? Because remember that this tells us that T1 is actually equal to 5 times T2. So that's one of the equations. Second equation, we can use the output torque. Right, so our first equation, from the belt tension, from the tension ratio, we can tell that T1 is equal to 5 times T2. Right? But we also know that in terms of torque is equal to the effective tension. Effective tension is T1 minus T2. So effective tension times the radius of the pulley. Now here we haven't been given the radius, we've instead been given the diameter of the pulley. But we know that the radius is equal to the diameter divided by 2, right? Now we have two equations, hence we can solve these simultaneously, right? So T out, we've just calculated, it's 560 equal to, and then from the first equation, T1 is equal to 5 times T2, so minus T2 times the diameter of the smaller pulley is 0.42 divided by 2, right? So here we have 560 is equal to, now taking care of the brackets first, 5 minus 1 is 4, and that 4 times this gives us 0.84 T2. Now you divide both sides by 0.84, hence making T2 the subject of the formula. So that means T2 is equal to, so 560 divided by 0.84 is 666,667 newtons. Right, so always make sure, right, you round off your answers to 3 decimal places, right, unless of course stated otherwise. So now you have T2, and then to get T1, therefore means T1, substituting it back to the first equation, it's 5 times 666,667, and then if you punch this in your calculators, we get 3,333,335 newtons. Right, and as far as belt tensions, we now have T1 and T2. Right, and for this case, this is how you'd approach it. Right, now let's look at 4.4. Right, this is where things now get interesting. 4.4, they want us to calculate the bearing reactions in the vertical plane. Right, they want us to calculate the bearings, right, along the vertical plane. Right, so this is 4.4. Right, and 4.4, they want us to calculate the bearings at their reactions along the vertical plane. Right, so this is where you now have to determine the forces that the mechanical systems, in particular the belt drive and the gear drive, right, how they are acting Right, you have to determine how they're acting on the line shaft's Cartesian plane. Right, and then after having determined that, you of course look at if looking at the Cartesian plane of the line shaft, are they at an angle relative to the Cartesian plane, or are they parallel with one of the axes? So looking at this here, the alignment of the mechanical systems, if you look at the belt drive, it's an angle of 70 degrees from the y-axis, which means our belt force will be at an angle of 70 degrees from the y-axis in the first quadrant. Right, that one is pretty straightforward. The one that is, or that can be tricky, is the normal force for the gear system. Right, so let's first determine the normal force. Right, let's first determine the normal force. See where it is acting relative to this Cartesian plane. Right, relative to this Cartesian plane. Right, so the first thing you do is you look at the configuration of your gears. So looking at your pinion. Right, is the pinion at the bottom? Is it at the top? Is it more on the left or more on the right? So in this case, the pinion here is at the bottom. Right, so bearing that in mind, you draw your Cartesian plane. Right, so the Cartesian plane for the belt drive. Right, so this Cartesian plane is for the belt drive, not the line shaft. So this is for not the belt drive, the gear drive, sorry. Right, so this is for the gear drive. Right, here you have the gear wheel, and then you have the pinion. Right, of course these two are meshing. Right, so in drawing this diagram, you must make certain that you position your pinion based on how it is positioned here. Right, so looking at this schematic illustration, the pinion is at the bottom, not the top, not the left, nor the right. So you draw this diagram making sure that the pinion is at the bottom. Right, now you look at the direction of rotation of the pinion. Right, they did say that the pinion is rotating clockwise. Right, so the pinion is rotating clockwise. That means it is headed in that direction. Right, now we can establish the direction of the tangential force as well as the direction of the radial force. Right, by looking at the direction of the pinion and asking ourselves, how would the tangential force have to act, or in which direction the tangential force would have to act, right, so that the pinion rotates clockwise. Right, remember that tangential force is the force that has to be applied for the pinion to initiate rotation. Right, that is why we base the direction of the tangential force on the direction of the pinion, or the rotational direction of the pinion. So if the pinion is rotating clockwise, it means this force, or the tangential force, would have to be acting such that it is headed towards east or the right. Right, so if it is acting in this direction, it would then push the pinion to rotate in a clockwise direction. Hence, the gear wheel would be rotating in an anti-clockwise direction. So now we have established the direction of our tangential force, which you then draw on the gear wheel. Right, so this here is the tangential force, hence if we were to consider the radial force, it will be here, and then our normal force being the hypotenuse of the two would then be acting in this direction. Right, so this here is the normal force. Remember, initially it is acting at 20 degrees, or relative to the Cartesian plane of the gear system, it is acting at 20 degrees. But remember here, we aren't looking at the normal force or where it is acting relative to the Cartesian plane of the gear system, but we are looking at where it is acting relative to the Cartesian plane of the line shaft. So having drawn or having established the direction of the normal force by just looking at where it is acting relative to the Cartesian plane of the gear system, we now have to align the normal force such that we know exactly how or where it will be acting if we superimpose it onto this schematic illustration. So the way you do that is you look at how your gear system is aligned here, and the way it's aligned is such that it is making an angle of 60 degrees from the x-axis in the third quadrant. So which means if this is 60, it means this angle here is 30 degrees. Bearing that in mind, that then tells us that in order to get this to align the same way as the schematic illustration that we've been given, we'd have to rotate this by 30 degrees clockwise. Right? Remember that this here is the Cartesian plane of the line shaft, right? And how the belt drive is aligned is such that it must align with this line, which is 60 degrees from the x-axis in the third quadrant, right? So essentially, to align what we have here, so just bear in mind that once you've established where your normal force is acting, you can now get rid of these two components. The two forces we use to establish where the normal force is acting. Once that is established, essentially you no longer need them, right? So what I mean by superimpose is you want to align the Cartesian plane of the gear system with how it is aligned in or on the Cartesian plane of the line shaft. And how it is aligned is such that it is such that the Cartesian plane of the gear system is making an angle of 60 degrees with the x-axis of the Cartesian plane of the line shaft, right? And as such, as you can see here, the normal force will then be in this quadrant. So it is important that you know exactly what this angle is, right? Or if you want to reference your angles from the y-axis, know what this angle is, right? So that's what I mean by superimpose. Now, in knowing exactly what that angle is, or where the normal force is acting relative to the Cartesian plane of the line shaft, you simply look at how you would need to rotate the Cartesian plane of the gear system such that it aligns with this line, right? And as we've established, we'd have to rotate it by 30 degrees. So from here, rotate it 30 degrees clockwise. So from here, you would rotate this by 30 degrees clockwise. That way it aligns exactly with this line. Hence, the alignment then suits the schematic illustration that we've been given. Now, if you have to rotate this by 30 degrees, essentially you are also rotating the normal force by 30 degrees. So bearing that in mind, it means if you were to rotate this by 30 degrees clockwise, right, you would have to rotate this by 20 plus 10, that is 30 degrees, which essentially means that based on the alignment given in our schematic illustration, the normal force is actually acting at 10 degrees relative to the Cartesian plane of the line shaft. So essentially, this is what we have. So this will be acting at 10 degrees from the x-axis of the Cartesian plane of the line shaft in the fourth quadrant. Right? Once that is established, now you can say now you can tell that the normal force is actually at an angle with the Cartesian plane. Hence, in having to calculate the reactions at the bearings, you'd have to resolve this into its components so that you are able to apply conditions of equilibrium, right? But before resolving this into its components, let us look at how you would determine the belt force. So essentially we are done with the gear system. Now we are going to look at the belt drive system to establish the belt force. Right. Now again, based on our schematic illustration, the belt drive is aligned such that it is making an angle of 70 degrees with the y-axis of the Cartesian plane of the line shaft, which means if you were to reference the angle from the x-axis, it means that the belt drive is aligned such that it is making an angle of 20 degrees with the x-axis in the first quadrant. Essentially, that tells us where the belt force is acting relative to the Cartesian plane of the line shaft. Right. So our belt force is acting somewhere there. So this is our belt force. Remember, making an angle of 20 degrees from the horizontal. Right. Having established this, now you can resolve these into its components. You've established that both forces, so the belt force and the normal force, are acting at an angle with the Cartesian plane of the line shaft. That means you have to resolve both into its components. So resolving both into its components, right? So you're going to have the belt force, the horizontal and vertical components. Right? So this being the horizontal component of the belt force, this will be equal to the belt force cos 20, and then this one will be the belt force, the vertical component of the belt force, which is belt force times sine 20. Right, those are the two components which will then be able to use in applying conditions of equilibrium. Now we do the same thing with the normal force. With the normal force, you have the horizontal component, and then you have the vertical component heading downward. So which means that the normal force, or the horizontal component of the normal force, so Fnh, is equal to the normal force cos 10 degrees, and the vertical component thereof will be the normal force sine 10 degrees. Right, so essentially on the line shaft's Cartesian plane, these are the forces that we have, right? And then also bear in mind that you have the flywheel, so you're also going to have the weight of the flywheel acting downward. So we also have a force there. Right, which is the weight of the flywheel. So this represents the weight of the flywheel. So as far as the Cartesian plane of the line shaft, these are the forces that we are going to get on it. Right? Having established that, now we can calculate the belt force as well as the belt force as well as its components, and then we've already calculated the normal force, so we just need to calculate the components of the normal force. Right. Now starting with the belt force. Remember, with the belt force, we have to consider the angle of contact. Our angle of contact is 160, which is less than 180, which means to calculate alpha, right, we are going to use the expression of how to calculate the angle of contact for a small pulley. Right. Remember that this is equal to 180 minus 2 alpha, and then making alpha the subject of the formula from this expression, we get 180 minus the angle of contact, right, divided by 2. So this is equal to 180 minus 160 divided by 2, which is 10 degrees. So alpha here is 10 degrees. Once that is established, we know that our belt force is equal to T1 plus T2 times cos alpha. Right, and as far as T1 and T2 Right, T1 is 3,333,335, and T2 is 666,667. So then this is equal to 3333,335 plus 666,667 cos 10 degrees. And if you punch this in our calculators, we get 3939,233 newtons. So that's the magnitude of the belt force. Right? So after having calculated the magnitude of the belt force, remember that for 4.4 we are calculating the reactions at the bearings along the vertical plane. So here we are going to consider forces that are parallel with the y-axis. So as far as the belt force, we are going to consider this component, FPV, of the belt force. So we have to calculate this here. So calculating FPV, and FPV is equal to this, which is equal to 3939,233 sine 20, which if you punch in your calculators you will get 1347,297 newtons. Right, so that's the vertical component of the belt force. Now let's calculate the vertical component of the normal force, right, which is this one here. Now take note here that I wrote this as positive even though it is heading downward. The reason for that is how you use this belt force, this component of the normal force, how you use it in applying conditions of equilibrium will determine whether you express it as negative or as positive. So meaningly, in applying conditions of equilibrium, if you use the law of moments, right, because with law of moments you essentially consider clockwise and anti-clockwise moments, right, and either of those will either be on the left hand side or the right hand side. Hence you don't write it as negative because of how we consider the direction. But when considering conditions of equilibrium for sum of forces, right, in a certain direction are equal to 0. So in this case, if we were to say the sum of forces in a vertical direction are equal to 0, only then you would then use this as negative, right? So just bear that in mind. Right, so calculating this component of the normal force. The normal force, remember, we calculated right at the beginning. So this here is our normal force. So normal force is 1418,903. So sine 10 degrees, and this is equal to 246,390 newtons. Right, so then now we can also calculate the weight of the flywheel, which of course is the mass of the flywheel times G. The mass as given is 200 kgs. So this is 200 times G, which is 9.81 for Mechanotechnics, and this will be equal to 1962 newtons. Right. Now we have determined all the forces acting parallel to the y-axis or the vertical plane. So now we can determine the reactions at the bearings. Right. But before we do, let us do this. Right, show the forces, show all the forces acting on the line shaft from a vertical perspective. Right, so those forces will be, so you have the belt force. Right, the belt force, remember, is acting upward, so this will be upward, right, this will be upward, and that belt force is 1347. Right, this is, where's the thing? Oh yeah, there it is, 1347. So this is 1347, 297 newtons. It's acting upward, and then the weight of the flywheel is acting downward. That one is 1962 newtons. And then as far as the normal force or the component thereof, so just take note here, in the diagram or in the beam illustration, there is a mistake. This wasn't supposed to be there. Right, so this wasn't supposed to be there. Instead, it was supposed to be on the left or on the right bearing. Right, this was supposed to be on the right bearing. Right. Now, as far as the component of the normal force, it is acting downward. So we say that you have a force acting downward here, which is this 246,390 newtons. Right, so as far as the vertical plane or forces acting parallel to the vertical plane, these are all the forces. Right, so now we can take moments. In taking moments, we're going to take moments about the right bearing. Right, so we are going to take moments about the right hand bearing, so we can call it RV, right, V for vertical. Hence, we are now going to, in applying conditions of equilibrium, using law of moments, the sum of clockwise moments is equal to the sum of anti-clockwise moments. Right, now let's look at the turning effect of each of these forces when taking moments about the right hand bearing. Right, so this one will have, right, the left bearing will have a clockwise turning effect. So this is clockwise. Right, the belt force will have also clockwise turning effect. The flywheel, right, will have an anti-clockwise turning effect. So this one is anti-clockwise. And then this component of the normal force will also have a clockwise turning effect. So this one is clockwise. So 1, 2, three of these forces have a clockwise turning effect, whereas the weight of the flywheel has an anti-clockwise turning effect. Right, so here on the clockwise side of things, we have the left hand bearing times the distance between the left bearing and the right bearing, which is 600 millimeters. So that's 600, right, plus the 1347,297 times the distance between the belt drive and the right hand bearing, which is 500. So times 500 plus the 246,390 times the perpendicular distance, which is 400, times 400. That is equal to the anti-clockwise moments, which are the weight of the flywheel, which is 1962, times the distance between the flywheel and the right hand bearing, which is 200 millimeters. Right. I made a mistake here. Right. The distance here is 800, so this is supposed to be 800. Right. This one is 500. That's correct. This one is 400. That's correct. And this one is 200. That's correct. Yeah. Then from here, you can now calculate. In fact, we can call this LV. Right. So the left hand bearing along the vertical plane. So the V stands for vertical plane. Right. From here, you can take any approach, right, that works for you mathematically. Right. I'm going to take the most convenient approach, which is to say that the left hand bearing along the vertical plane is equal to, so you'd have to transpose, right, these terms to that side, which means you're going to have this minus both of these terms. Right? And then, of course, all of this divided by 800. Right, which is this 800. Right. Now, if you punch this in your calculators, right, this will be equal to negative 474, 756 newtons. As you can see, this is negative, but remember, the negative sign shows us the direction. So seeing that this is from a vertical perspective, it means the reactions on the left hand bearing along the vertical plane is acting downward. So which means this is 474,756 newtons, and the direction is down. Right? So now we have LV. So now we can calculate RV. And the way you calculate RV will be up to you. At this point, you have the option of either using the law of moments or the sum of forces along the vertical plane, which is what I'm going to do. Right, so I'm going to consider the sum of forces along the vertical plane being equal to 0, because the forces are in equilibrium here. Take note. All right. So considering forces along the vertical plane being equal to 0, this is how I'm going to get my RV. Now, just take note that initially you always assume that the reaction at the bearings are headed in a positive direction. But initially, this is what you always assume, that the reactions at the bearings are headed in a positive direction, and then your calculations, of course, will then confirm if really the reactions are headed in the positive direction or the negative one. Now, for the case of the left-hand bearing, initially it is assumed that the reaction is headed in a positive direction, but our calculations just told us that actually it is headed downward, the negative direction, right? So in applying this condition of equilibrium, just bear in mind we now have to take this as being negative, right? So starting from the left heading to the right, you have your left bearing. Your left bearing is negative 474,756, right? And then you have this component heading upward, so positive 1347,297, and then you have your flywheel heading downward, so negative 1962. RV, remember initially we are assuming that it is headed upward, so you take it as being positive RV, and then this component of the normal force is heading downward, so minus that 246,390. Right, now if you punch this in your calculators, if RV, right, minus, you should get negative 1335,849 is equal to 0. Therefore, meaning RV is equal to, you obviously transpose this to the other side, and it becomes positive 1335,849 newtons. It is positive, which means indeed it is headed up. Right, we have determined LV as well as RV. That's the reactions at the bearing along the vertical plane. Right, now let's look at 4.5. Right, 4.5, they want us to calculate the bearing reactions in the horizontal plane now. And so looking at the reactions at the bearings along the vertical plane, this is 4.5. All right. Now remember, at this point, you've already established all your important forces. Right? You already know where each of the forces or the components thereof are acting and in which direction. All right. So all that's left to do really is to show that on the beam for context. All right. Show those forces on your beam for context. Now, bearing in mind that we are now looking at the reactions at the bearings along the horizontal plane. Right. Now you have two choices here. You can draw your beam horizontal, right, and then take things from there. But what I'm going to do is to draw the beam horizontal. Right, to show you the easiest way of doing this without having to draw the beam vertically, right, which essentially we never do. As the way you do that is you just take into consideration that forces that are heading left, you take, remember, as negative. And then negative forces, right, when the beam is horizontal like this, we take negative forces as heading downward, and we take positive forces as heading upward. So that is to say that for 4.5, forces that are going to the left, we are going to draw here heading downward, and then forces going to the right, we take as positive, hence we are going to draw here as heading upward. Right, you can take that approach, it's much easier, or you can simply draw the beam vertically. Right, that will work as well. Right, it's going to look weird, but it is going to work. Right. Right, now considering the forces, so the belt force, it's going back to a Cartesian plane. So as far as the belt force, we have this component. It's headed to the right hand side, which is positive, which means, seeing that it is positive, it means that it is headed upwards. Right, FBH, component of the belt force along the horizontal plane, which is the belt force. Remember, we did calculate, and it is equal to 3939,233. So this here is 3939,233 cos 20. Punching this in our calculators, you should get 3701,668 newtons. Right? Then, of course, you look at the horizontal component of the normal force, which is this one. Right, remember the normal force we calculated and got the 1418,903. Right, so this is equal to 1418,903 cos 10. Punching this in our calculators, we should get 1397,347 newtons. Right, now remember that the horizontal component is headed to the right, which is a positive direction, which means here, remember that this we do not have. This was a typo. This is actually supposed to be right there. Right, now our component of the belt force is headed right, which means it is heading upward. Right, so this component is 1397,347 newtons, and the belt force component is 3701,668 newtons. Right, so remember that the flywheel, the only force to consider there, right, the only force to consider as far as the flywheel is its weight. Right, its weight is parallel with the vertical plane. There is no component of the weight that is parallel with the horizontal axis. Hence, there is no force to consider as far as the flywheel along the horizontal plane. Right, so now we take moments. Right, so now we take moments about the right hand bearing. So now we are going to call it RH, seeing that we're considering the horizontal plane. All right, sum of forces, sum of clockwise moments is equal to the sum of anti-clockwise moments. All right, so now we look at the turning effects of each of these forces. All right, the left hand bearing will have a clockwise turning effect. This will also have a clockwise turning effect. and then this will have an anti-clockwise. So this one is anti-clockwise. That one will have an anti-clockwise turning effect. And so we have on the clockwise side, you have the left-hand bearing times the distance between the two bearings, which is 800, right, plus this component of the belt force, which is 3701,668 times the distance between the belt drive and the right-hand bearing, which is 500. And then of course this is equal to this here. The only force that has a anti-clockwise turning effect, so the 1397,347, right, times the perpendicular distance, which is 400. So times the 400. Right, then from here, remember this is LH. So LH is equal to, so this then minus this term, and of course we divide all of this by 800, which means LH, if you punch this in your calculators, will be negative 1614,869 newtons. Now bear in mind that we are now looking at the horizontal plane. So negative forces, we take them as heading left. Positive forces, we take them as heading right. So this one in particular is negative, which means that actually LH is 1614,869 newtons heading left. Right? Now to calculate RH, we're simply going to calculate the sum of forces along the horizontal plane. Right? Sum of forces along the horizontal plane we know are equal to 0. And now we just simply add all of these forces that are along the horizontal plane. Right, so those forces include the left-hand bearing, which we have established that it is heading left, not right, as initially what is this thing? As per the initial assumption. So this is heading downward, so it is heading left, hence you take it as negative. So this is negative 1614,869. Then we have this force, which is heading right, so you take it as being positive. So this will be positive 3701,668. And then we have the right hand bearing RH, which initially we assume is heading right, the positive direction. So plus RH. And then we have this component, which is also heading right, the positive direction. So plus 1397,347, and all this is equal to 0. Now from here, RH, and then if you add all of this, we get positive 3484,146 is equal to 0. Therefore, meaning RH, transposing this to the other side, will be negative 3484,146 newtons, which means this is actually 3484,146 newtons, headed in a negative direction, which along the horizontal plane is left. Right, so both our reactions along the horizontal plane are headed left. Right, and that is how you would approach this, or this is just one of the ways you could approach this. Another way you could have done it, of course, is again using the law of moments here to determine RH by taking moments about the left-hand bearing, LH. Either way, you're going to get the same thing. Right? Now let's look at 4.6. This goes up to 4.6. 4.6, they say calculate the resultant reactions on the bearings. So it does not always happen that you are asked to calculate the resultant reaction, but in a case where you have to, I'm going to take you through how you would do that. So this is 4.6. Right, and the way we do it is by simply applying what we learned when we did laminas. Right, when we did laminas in engineering science N3 as well as N4. Yes, I am taking you back to engineering science N3 and N4. Right, so we are going to apply what we learned when attempting problems based on laminas in engineering science. Right, so the way we do that, easiest way of doing it is you consider the reactions on the left hand bearing as well as the right hand bearing from the perspective of the reactions along the horizontal plane and the reactions along the vertical plane. So meaningly, first considering the left hand bearing, so let's say consider resultant for left bearing. Right, so we're going to call this one RL. Right, so resultant for left bearing. Right, now if you look here, you have the component of the reaction going, or that is acting along the horizontal plane, that is LH. So if you go to LH, LH is headed left. Right, you go to LH, LH, where is it? LH is headed left. Right, so which means you have LH heading left. This here is LH. And then you look at what is this? LV. Go to LV. LV is heading downward. So which means something that looks like this, that's LV. Which means the resultant reaction on the left hand bearing is acting somewhere there. This is RL. Right, so we do the same thing on the right hand side. Remember, we don't have this. Instead, we have that. Right, now we consider the right hand bearing and look at RH as well as RV. Right, as far as RH, it is headed left. RV is headed up. So which means you have your RV and then you have your RH, which means the resultant of the right hand bearing is acting somewhere there. This is your R, the resultant of the right hand bearing. So when they say calculate the resultant reaction, this is what they're looking for, right? Which you simply just use Pythagoras, right? Using the components in the Pythagoras, and then you will have determined the resultant. So meaningly here you will have, for instance, RL. RL has two components, LH and LV. Right, so you have, for instance, here LV squared plus LH squared. Right, so this will be equal to right, what is LV equal to? LV is the 474,756, and then LH is this 1614,869. So now you substitute LV is 474,756. Remember, all this is squared, plus LH, which is 1614,869 squared. Right, so all of this is under square root, and if you punch this in your calculators, you should get 1683,210 newtons. Right, and then now we consider the right bearing. So considering the resultant for the right bearing, this is R. Right, to calculate RR, you simply again apply Pythagoras. Right, so this will be RV squared plus RH squared. So this is equal to so RV is the 1335,849, and then RH is the 3484,146. So now you substitute. This is RV is 1335,849 all squared plus RH, which is 3484,146 squared. Right, all this under square root, and this should be equal to 3731,456 newtons. And that is essentially how you do it. Right, so this exercise, I chose to do this exercise because it essentially covers everything regarding line shafts. So any and everything that you could be asked to calculate. Right, it is not always the case where you are asked to calculate all of this, right? But this is essentially everything that you could be asked to calculate. I hope you found this video very helpful. Stay tuned for more videos on line shafts. I'm thinking I might be doing 1 or 2 more calculations before I move on to other topics. Right, so if you liked this video, just make sure to hit the like button, right, and also share the video with your fellow students. Right. Happy studying. Cheers.